Okay, there are two three-dot problems in Chapter 7 that we're looking at. The first one is number 33. We're basically pulling a block on a spring. Shockingly enough, not the same problem, but almost the same problem we've done like 3 times already. And they're asking variations on where does it stop, how much work is done, what is its maximum kinetic energy, things of that nature. Basically, the question you have to ask yourself here is, what is the condition for this thing to stop? The two tempting options that most people are going to want to jump to are when the forces are balanced or when the total work is equal to 0. So I don't want to answer that question because that's kind of the crux of this. But you should be able to ask yourself, when the forces are balanced, is that the farthest the block will go? Similarly, you should be able to ask yourself when the total work is 0. So that means when the work from the applied force and the work from the spring are balanced, will that mean that the block has stopped? We've talked about this a little bit in class as we've worked through some examples. So I don't think there's too much more I want to say about this one. As for number 42, 42 is a little more sinister. So we've got a pulley, a block, and it's being pulled by this tension that's at an angle. So as you are pulling it, and you want to find the change in kinetic energy, so as you're pulling it, you have the slight problem that the direction of the force changes. So basically, as it's pulled, this angle is going to change. So if you wanted to write out your work as a integral expression, you have an implicit dependence on x inside of theta. The answer to this I would recommend doing is some good old-fashioned right triangle trig. So, you know that this is theta, this is x, this is h, this is then the square root of x squared plus h squared. So, you know that cosine of theta is then, drumroll please, x by root x squared plus h squared. Which I probably could have made look less horrible than that by scrolling up ever so slightly. That's still going to give you something of an ugly integral, but it is at least doable. It's tabulated, it's not like super exotic. There is, however, a non-calculus and exceedingly clever way to do this. And that is to kind of look at it from a big picture. If we look, you have to be pulling the rope from over here. So someone is exerting a force T on the rope and pulling it over the pulley. So how much rope is pulled over the pulley as it moves from x1 to x2? This L1 minus L2, as I've defined it here, is the amount of rope that's pulled over the pulley. And so since the rope is being pulled at constant force, and this is the displacement effectively, that's the amount of rope that's been pulled over, you could just say this. But you should actually do the problem and not just take my word for it. Hopefully that gets you started and gives you something to work on. Good luck.